All right, so it's my pleasure to introduce you today to Silouanos Brazitikos from University of Athens. He was already here in Zaragoza last year before the pandemic started, when we went to Monzón in the EITA meeting. And well, today he's here virtually and he's going to talk to us about vector valued Maclaurin inequalities. So whenever you want.
So, David, thanks a lot. It's my pleasure to be with you all, and I hope that next time it will be in person.
Yeah.
This is joint work with Finlay McIntyre from the University of Edinburgh, and this work will be up to archive, I think, around Friday. We upload it today, so it is something fresh. And I hope that you will enjoy it. Well, the topic is about the Maclaurin inequality. And the classical Maclaurin inequality compares consecutive symmetric sums, which means that we have some positive real numbers, let's say m of them, and we compare the k symmetric sum, which is the sum of all of k products of these m numbers, and these are, of course, m choose k, and the Maclaurin inequality compares these two means, and it says that the k minus 1 mean is bigger than the k mean. Okay, and of course, this is a stronger inequality than the arithmetic geometric mean, because all these means are between the geometric mean here, which is the product to the power 1 over m. Here are all these intermediate terms, and the biggest one is the arithmetic mean. Our idea was to try and generalize this Maclaurin inequality, and we first replaced the numbers with vectors, and the second thing we have to do is replace the product with something else. So we replaced the product with wedge product. And what's the wedge product? It's if we have m vectors in Rd, then for any k of them with k smaller than or equal to d, we denote the wedge product of the absolute value of the wedge product of these k vectors to be the k-dimensional volume of the parallelogram spanned by V1 up to Vik. And so using all these lead us to ask for the following generalization. So also here you will see that we replaced the numbers with vectors, the product with the wedge product, but also we put it also the mean. So we took all these term here to the power p, and well, these in the case of numbers, this doesn't change the quantity at all. if you put the numbers to the power p, but now for different p, we have different inequalities. And the problem is, in some cases of p are easy, and some cases of p are hard. And also note that if the vectors are orthogonal, then this wedge product becomes the product of the lengths of the vector, so we can apply the classical Maclaurin inequality. So this inequality implies the classical Maclaurin inequality.
Okay, so sorry, one question, if possible. So this includes the fact that this wedge product could be zero because there is no, depending on the position of the vectors, right?
Right.
That allows being zero for.
Yes.
But it is general.
It can be zero also, yeah.
Okay.
So we can prove this conjecture for in the following cases. The first case is p equals 2. The second case is p equals 0. The other case is p equals infinity. I will explain what means p equals 0 and p equals infinity. And when p equals 1, we cannot do it for all k, but we can compare when k equals 2, 3, and d. Okay, let's first see the p equals 2 case. So we denote a square matrix with columns V1 up to Vd. And let's say that its eigenvalues are lambda 1 up to lambda d. Then we defined the submatrix of this matrix. So we take some indices I1 up to Ik, and we define the matrix BI1 up to Ik to be the matrix with columns Vi1 up to Vik. And so this is the left-hand side of the quantity that we would like to bound. Note that we can write this like, so its wedge product, the power 2 is exactly the determinant of the transpose of this matrix B times the B matrix. So this is an equality. And then note that if we consider the matrix A transpose A, then its matrix B transpose B is a principal minor. So we will use here that the sum of the principal minors is the symmetric sum of the eigenvalues. So we have from linear algebra, we have this fact here, this equality, which is, well, it's not trivial, but it's not hard also. Now the nice thing that we are back to numbers. So these eigenvalues are from A transpose A, for example, and so we can, they are real numbers. We can apply the classical Maclaurin inequality to compare the k mean with the k minus 1 mean. And now we can go back now. So we can write it back as the sum of the minors of the k minus 1 minors now. And this is equal exactly to, like in the first equality with the k minus unfold wedge products, the sum square, etc. So that's really the proof for p equals 2, but this proof is only for p equals 2. I mean, this only fits in that case because we have this nice identity here from the linear algebra only in this case. So this works because this wedge product square can be written as exactly the minor. Okay, so we cannot use this proof for any other value of p. Now we are going to see the cases p equals 0 and p equals infinity. For these cases, we will use an inequality of SAS, which is about principal minors. And it says that if we have an n by n matrix M, and we take some k between 1 and n, then we have the following inequality. The product, and here with M index A, we mean the minor which comes indexing the columns of M by a set A which has cardinality K, and the same thing here. So this inequality really compares such things, but it compares the products. So this fits to the case immediately to case p equals 0, because when we have a mean for p equals 0, then this becomes a product. So again, to prove the p equals 0 case, we take the matrix with columns v1 up to vm, and again we take a i1 up to ik, the matrix with columns vi1 up to vik, and then as before we have this this equality. And now we observe also, like before, that i1 up to ik transpose times this matrix again is a principal submatrix of A transpose A. So we can use SAS lemma to get this inequality. So we compare exactly here the cardinality is K. We take all these principal submatrices with matrices with cardinality K, and here with K minus 1. So SAS inequality says exactly this thing here. And we can rearrange this taking square roots and playing with the binomials here like this, and this is exactly the equals 0 case. Okay, so that was the p equals 0, and the equals infinity is also also follows from SAS inequality, but in another way. I mean, to do the following here. So you start with now. Let me say that in the case p equals infinity, the p mean of the numbers becomes the maximum. So here we would like to compare the maximum of all k-fold wedge products with the maximum of the k-1 fold of the wedge products. So we take the indices I1 up to ik where this is maximum. And we use such inequality to compare this with we take n equals k, and we just forget about only one column. And the such inequality says exactly this. And now these are k-1 fold wedge products, and we just bound them by the it's term of the product. We bounded by the maximum. And this is enough because this becomes the maximum of k-1 fold wedge products to the power k, because we have just k terms here. And so rearranging, we get, if we raise everything to the power 1 over k here, we get that the maximum of the k-fold wedge product to the power 1 over k is smaller or equal than the maximum of k-1 fold wedge product to the power 1 over k-1. So that was the case p equals infinity, and these were the, let's say, the easy cases, the p equals 0 and p equals infinity. And let's go the p equals 1 case. So p equals 1 cases are different than 2, different than 0, different than infinity. I will need here the notion of mixed volumes to make all the comparisons, etc. So let's introduce the mixed volumes. These are introduced by a theorem of Minkowski, which exactly describes the way that the volume behaves with respect to addition and multiplication of compact sets by non-negative reals. So if we have some k1 up to k capital are convex bodies in Rd, then we take the Minkowski sum of this combination T1 k1 plus Tn kn, and we take the volume of this Minkowski sum. And this theorem of Minkowski says that this is a polynomial in Ti's. So it is a homogeneous polynomial of degree d, and the coefficients that appear here is what we say mixed volumes of convex bodies. So exactly this coefficient is called the mixed volume. So this is exactly what mixed volume is. And some very basic properties is that a mixed volume is positive linear with respect to its arguments, and of course, if we have the same convex body in all positions, then the mixed volume is the volume, is the d-dimensional Lebesgue measure of K. Okay, and now we are going to Steiner's formula, where instead of taking many convex bodies, we take a convex body K and a multiple of the unit Euclidean ball in Rd, which is B2D here. And as before, Minkowski sum of k plus t b2d is a polynomial in T, and the coefficients here that appear have another name. We say that these are the coefficients that corresponds to the t to the power k is the k Quermass integral of k. And it is exactly, of course, the mixed volume of taking d minus k times d minus k times the convex body k and k times the unit Euclidean ball. And one more let's say multiple of the Quermass integrals is the k intrinsic volume of a convex body, which is defined to be this here. So here in maybe the most important inequality which has to do with mixed volumes is the Alexandrov-Fehel inequality, which is the Deep Theorem, and it says that well, if we suppose that we have some convex bodies, d of them, and let's say that we fix k3 up to kd, and we make this mixed volume here to square, and here the other side we have we replace we have the same in the first two positions. Here we put 2 times the convex body k, and here we put 2 times the convex body L. And that's the Alexandrov-Fehel inequality, which implies, which is easy to see, that implies also that this inequality about intrinsic volumes. So this says exactly that if you take the j minus 1 intrinsic volume of k over the j minus 1 intrinsic volume of the unit Euclidean ball, then this is to the power j. This is something which increases with the index. So this, let me say that this inequality, for example, contains many well-known inequalities. For example, the simplest case is the when j, for example, equals d, then it contains the classical isoperimetric inequality because the intrinsic volume, the j minus 1 intrinsic volume, has to do with the surface area. So, but let's see how these are connected with our problem. So let's see how these all things has to do with our problem. The main theorem that we're going to use is this theorem of Schneider, which says that if we have j zonoids, and I will explain what is a zonoid next, with generating measures row 1 up to row j, and we have d minus j convex bodies, then there is a formula that computes exactly the mixed volume of having in first j positions the zonoids and the next d minus j positions the convex bodies. So we have some factor here, and then we integrate the wedge product of j of j vectors. Here we have the mixed volume of the projections of convex bodies to the span, the orthogonal to the span of u1 up to uj. So zone on top Z in RD is a sum of segments. So for example, in R2 is a polytope. And what is a zonoid? It is it's continuous analog. It is, let's say, the limit of is a limit of zonoids. So we will use this in some particular case, because in our case, our zonoid is a parallelotope. We consider a parallelotope with edges V1 up to Vg to the directions of the unit normals V1 over the norm up to Vd over the norm of Vd. And this is exactly the sum of the segments that VIs generate. So using the previous formula, doing some computations, I'm not writing them here. We have this equality that the K intrinsic volume of the parallelotope is exactly the sum of the K-fold wedge products. So this is the connection now of the sum of K-fold wedge products with the intrinsic volume. So we can rewrite now our conjecture as follows. So in this language, our conjecture is an inequality for intrinsic volumes of parallelotopes. So it says that the intrinsic volume of the parallelotope over d choose j, which is let me say here that this here is exactly the intrinsic volume of the cube, is at most the j minus 1 intrinsic volume of the parallelotope over d over d choose j minus 1, which is the vj minus 1 of the cube. So we have, and the equality holds if and only if P is a cube. And you can see now that this is an Alexandrov-Fenchel type inequality. So remember that in Alexandrov-Fenchel here we had the intrinsic volume of the ball. So here this says that if we restrict ourselves to parallelotopes, then the extra measures to the Alexandrov-Fenchel inequality is not the ball but the cube. This is what our conjecture says. in the case always we are in the case p equals 1. So let's see what happens in some particular cases. For example, in when j equals d, we can rewrite the previous inequality like this, and Vd is exactly the volume of P. This is 1, of course, and Vd minus 1 is a multiple of the surface area, as we can see here. Therefore, in this particular case where when j equals d, we have a nice supersymmetric type inequality, which says that among all parallelopipeds with the same volume, the cube has the minimal surface area, and this is the only case that it was known up to now, and that was proved by Hodfigger in the 70s, and he used symmetrization, but his proof works only in the case of volume and surface area, because we know that symmetrization, Minkowski symmetrization, keeps the volume and reduces the surface area. So after some symmetrizations, you are going to, from a parallelotope, you are going to, you stop to a cube. Okay, and let's see now what else can we say? As I said in the beginning, we can our proof gives this result of Hodfigger with another proof, but we also are able to prove other non-trivial cases, like comparing the third with the fourth mean and the second with the third one. But these are the only ones that we can do with a Sharp constant. Okay, now let's see a reduction here that we made for the case p equals 1. So here we just introduce this notation just to streamline the argument. So the sum of these k-fold products is denoted by sk. And what we would like to do is to construct a vector v1 tilde, which lies in the orthogonal complement of the span of v2 up to vd, such that sk is smaller than sk, and here we replace v1 with v1 tilde, and the sk minus 1 mean is bigger or equal than this one. And if we do this, then repeating the procedure, we can make all vectors orthogonal, and therefore reduce our inequality to the classical Maclaurin inequality. Okay, so let's write down what is this condition and what is the other condition. The first condition is exactly this one, and the second condition is exactly this one. So note now that V1 tilde is orthogonal to the vectors V2 up to VD. So if we take any R vectors of V2 up to VD, and we take the wedge product of V1 tilde with the other R vectors, then since Vi tilde is orthogonal to them, then this is exactly equal to the Euclidean norm of V1 tilde up times the wedge product of Vi1 up to VIR. So if we use this equality here, and we plug in here and here and here and here, we can see that these two inequalities can hold if the Euclidean norm of Vi tilde is between these two things here. Therefore, in order to prove the P equals 1 case, we just have to show that there is some number between them. So it's enough to prove that this is smaller or equal than this. Okay, and now we use again Schneider's formula to write down what is, like before, to write down what is this and what is this, what is this and what is this. And the reduction that we have is the following. So we take some m vectors in Rm, and we make also the zonotope from I equals 2 to m of the segments that UIs produce. And then the calculations says that the previous inequality that I wrote with the sum of wedge products is equivalent to this thing, which says that exactly if we take this ratio here of the projection of this zonotope to U1 perp over the intrinsic volume of the zonotope, then this ratio is decreasing. And a comparison of these quantities is known by the Fallen Theorem. So that was a theorem from 2000 of Yiannopoulos, Hartoulaki, and Pauris, which compares these quantities, but there were some disadvantages here, of course. The first disadvantage here is that this is a theorem for all convex bodies, while here we ask only something for zonotopes. And of course, if you're looking for all convex bodies, then you miss something in the constant. But the constant here is not that bad. It can be bound by an absolute constant which is smaller than 2. So using all these things, in the P equals 1 case, we can compare for any k the quantities between the wedge products. So we can show that for any t-tuple of vectors, the following inequality holds, and now we have here the sum of the k-fold wedge products over d choose k to the power of 1 over k, and we lose exactly the constant that we lose from a theorem of the previous theorem. And so we can prove the vector valued Maclaurin inequality, but not with the expected constant, which is 1. As I said, the only thing that I didn't prove here is the cases where k, when we compare this mean here with this mean here with sharp constant 1 and k equals 2, 3. The proof are geometric ones. And also there is a question for us that for any other value of p, we don't know anything. I mean, we don't know any connection of this means with something geometric, like in the case p equals 1. It would be interesting to find one. Maybe some, maybe a p sum of segments, but I don't know, some generalized mixed volumes. We didn't manage to find a connection for the other values of p. So thanks.
Okay.
Okay, so thank you very much for this presentation. If anybody has any question, you can unmute yourself.
Okay, so the proof p equal to 0 and infinity, the proof is algebraic.
Right, right.
P equals 1 introduces geometry.
Right.
Okay. By the way, you mentioned equality for some cases in the case p equal 1. Does equality cases for the other p say anything?
Well, yes, we expect that the equality case is when all vectors are orthogonal and they have equal lengths.
That's the only case.
Yes. So they make some cube.
Yeah.
Yeah.
In every, okay.
Oh, yeah. We don't have a proof of this fact, but we expect that these are going to be the only equality cases.
Okay.
And if you have your vector giving you a decomposition of identity, do you have something, or you have a family of vectors which form a decomposition of identity? Is there anything about that property that can give you a better constant or something?
No, unfortunately, and let me also say that when in the beginning I said about the conjecture, then I said that we take m vectors in RD.
Yeah, but you can take more, right? Or not?
Here, this proof gives only d of them, like the dimension, but maybe. I believe that in the case here with p equals 1, if we have more the vectors and some representation of the identity or something like this, then we can probably do something. But
like lifting the vectors, like you were taking another vector in an orthogonal subspace before, but maybe if you have a decomposition of identity, you can use this trick of lifting them to a higher dimension until you get an orthonormal basis. I don't know.
Yeah, I don't know. Well, I think that there are things to do here, but and of course for the other values of P, as I said, I mean, what happens with general P would be these are all open, and I think we can say something geometrically.
Okay, thanks. Are there any other questions? No? Okay, then I'm going to stop recording, and thanks again.